Okay, we have an interesting series here. Today we've got the sum from 1 to infinity of sine 1 over n to the k, where k is going to be greater than 1 and k is going to be an integer. So to get started with this, the first thing I want to deal with, I like to do this whenever I have something kind of unfamiliar, like a trig function inside of a sum, is I want to do the test for divergence to see what's going to happen when n is going to infinity, because if that limit does not go to 0, then the whole thing diverges and we have no other work to do. So let's do this check first, where we're going to check the limit as n goes to infinity of this thing. But you'll notice when n is going to infinity, this part right here is going to be going to 0. Sine at 0 is going to be 0. The k is not going to matter. And so this limit is just going to be 0. And now when this test is 0, what's going to happen is, if it was anything other than 0, it would be divergent. But 0 is inconclusive. We can't, just because it's 0 doesn't mean we can say it. Just because it's 0, we can't say that it converges yet. We just have to do more work. So we're going to get rid of this because that doesn't really help us. And so next what I want to do is kind of create something to compare this to. And let's just notice this other series, if we're going from 1 to infinity of 1 over n to the k, where this is going to be the same k we're using right here. Well, we know how to do this because we have the p-series for this. The p-series is going to tell us when you have 1 over n to the k, when k is greater than 1, this thing converges. When k is less than or equal to 1, this thing diverges. So because we have our condition right here that k is greater than 1, we know already that this thing converges. And what I want to do is I want to use the limit comparison test on this, comparing this to this, because when we do that, if we've got one thing we know, if the test passes, then this is going to have the same convergence as this. So in order to do this, what we want to do is we just want to do the limit as n goes to infinity of this thing and this thing. You can do this fraction either way. I think it's typically done this way, but it's not going to matter what you put in the numerator or denominator. And then from here, what I'm going to want to do is, in order to get this limit, because it's not obvious just looking at, I think, I'm going to want to break this up, again, knowing that our k is going to be an integer greater than 1. So we can write this in a different way. Writing it this way, we don't know how many terms we have. I mean, we know k has to be at least 2, actually, because we have k, we've got the same k in the numerator and denominator. And so now, all I really need to do is I just need to find the limit of one of these. All these are going to be the same. So if I just know the limit of this, then we know we can find our full limit. Well, in order to make this more familiar, I can do like a substitution. I can set m equal to 1 over n, and that's going to change the numerator and denominator. So when we do this, we're going to have our numerator becomes just sine of m, and then our denominator becomes just m. But now we want our limit in terms of m, not n. When n's going to infinity, m is going to be going to 0. So we can do this here as m is going to 0. But this right here is a really well-known limit. The value of this is just going to be 1. You could do this a few different ways. Usually it's done, like, I think, with the squeeze theorem to prove it. So there's a little bit of a proof to it. If you use L'Hopital's rule on this, you will get the right answer. But I think it's kind of circular reasoning, because I think the definition of the derivative depends on L'Hopital's rule. And so I don't think you're technically supposed to do it that way. But anyway, either way, you're going to have 1 for this limit. So coming back here, if we look at each of these individually, what you could do is you could write it all out and have the limit of this times the limit of this times the limit of this. But each of these values is going to be 1. So this whole limit is just going to be 1 for everything. And for the limit comparison test, what we want to check is, first of all, is this value greater than 0? And second of all, is this finite? Yes, it is. So this is going to pass the test. So this value is finite and not 0. So this is going to pass the test, which means our original sum is going to have the same convergence as what we have here. And so we can say that this also converges. Okay, there you go. Interesting case with the limit comparison test. Thanks everyone for watching. Have a good day.